Thanks, everyone. My name is Marlon Bazan. I am a principal at Protection Engineering Consultants. And I'm going to be talking about blast hardening concepts for existing buildings, but within the context of the document that Ganesh was presenting earlier, which is the 370 report. So one of the chapters talks about blast retrofits. So that's just the overview of the presentation. So I'm going to start with some introduction, some general recommendations, and then some examples of different retrofits and some final remarks. Now, before I go ahead with the presentation, I have to start with a statement. So this presentation is very general. It doesn't go into details. It doesn't go into equations. So for people that are familiar, the intent of this presentation was really, when we were talking with the organizing committee for this session, was the target audience was people that were not familiar with blast resistant design. So just to get them introduced to some concepts in terms of retrofits in general. So if you're familiar with resistant design, this is probably going to be way too basic. And the figures that are going to be here, probably you have seen it like 50 times at least, right, if you work in the industry. So I apologize for that. So now with that, so as I said, so I am part of the committee working on the task group, the subtask group working on ACI 370 report, and I was working on chapter 10, which is the update of chapter 10, which is for retrofits. Now that the updates on that retrofit were minor, relatively minor. It actually was a very well-written chapter. So just some minor revisions. This chapter covered different type of retrofits, including strengthening of existing elements and also employing additional elements. These include, structural elements, columns, floors, slabs, but also non-structural walls like CMU, reinforced CMU, unreinforced CMU, precast panels, and so on. Now, as I said earlier, this document provides a very general overview. You won't find one single equation in that chapter. Again, that chapter, I'm just talking about that chapter 10. You won't find a single equation in chapter 10. It's just general concepts. And so it's not supposed to be a how-to chapter or a how-to document in terms of how to design. It's more of just to present what are the options and then direct the reader to other references where you can find ways to and more details about these retrofits. Now, before getting into the examples of the retrofits, just wanted to give talk about some general aspects. So the first thing when you're going to choose a retrofit, right, you have to understand, why do you need to retrofit it? Is it because you're not meeting your response limit? And first of all, you have to make sure that you're using the proper response limits, right? Like Bill was talking earlier, right? And it depends if you are working with TFP and if you say TFP, if it's a DoD project, is it a VA project, is it a GSA project, and if it's explosive safety or if it's petrochem. So make sure that, why is the reason that you want to retrofit it? Is it because it's flexural, deficiencies, or is it because of shear deficiencies, or are you trying to protect the component itself, or you don't really care about the component itself, but what you care is about what's behind that element, behind that wall. So you have to understand that. Then you consider your retrofit options, and when you are considering all your options, you have to look at performance. Is that retrofit going to get you that performance that you want? Again, whether it's flexural, if it's shear. Feasibility also, you may do the analysis, it shows that it meets the criteria, but maybe you cannot build it because it requires access to the interior side of the wall, and the owner has equipment installed on the inside of the wall, and they don't want to remove it, or they can't remove it. So feasibility of construction, and the same thing could be if it needs to be installed on the exterior side of the wall. Cost efficiency, right? Because again, you can run the analysis and shows that it works, it might not be cost efficient. In some cases, it might be more cost efficient if it's not a structural member, just to tear down the wall completely and build a new one. And so that's an important aspect. Now, the last two are more like technical, more structural, and I think that those are the most important. and it's that when you have to evaluate the effect of the retrofits on other response modes. So what do I mean with that is that, as one example, most of these retrofits are for increasing the flexural capacity. But what happens is when you increase the flexural capacity of a member, you are increasing the shear demands. And if you don't consider that in the design, you may be introducing a failure mode that you were not accounting for. So if there is one takeaway from this presentation, it would be that one, I think. But then there's also evaluation of the effect of the retrofits on other elements as part more of looking at the structural system. Because you're changing the stiffness potentially depending on the type of retrofits, you're changing the capacity that may cause some load redistribution. For some of these retrofits, not all, you're maybe increasing the weight. For example, if it's shotcrete and you're adding concrete, then you might be increasing the weight. So now what about your foundation? Can your foundation take that? So you have to, again, not just think of that element, but the effect of retrofitting that element on other elements. And I guess, that's true for whether it's blast or it's seismic retrofit or any other type of structural retrofit, right? So now I'm just going to go through some examples of retrofits that are covered in this chapter 10. And this is just a few examples. Okay, the chapter 10 of the 370 report covers lots. So I couldn't include all of them in this presentation. This is just, I handpicked a few of them. So for columns, columns typically require a retrofit for closing detonations. In general, you could have a far range detonation that could overload your column, but in most cases it would be a closing detonation. Now, a far range detonation typically won't overload your column because your column, the amount of load or the tributary load, if you think in those terms, is relatively small, typically, right? Because column will just collect the blast load over its width, unless you have other elements supporting to that column, but that's not typical, or connected to that column. But for a closing detonation, there are different effects than for a far range. You have non-uniform load, you have local effects that could be even for modes that typically are not considered, not like even at an element level response like flexure, but more like local. You could have spalling, you could have scabbing, you could even have brisance where you essentially just pulverize the concrete. So possible retrofits for that, again, depending on the intensity or the magnitude of the blast load and how close it is to the column. So FRP wrapping, and this is one example of, this figure is taken directly from the ACI 370 report. This is a test done by KNC. And that column was, so on the left there's a column, original column without retrofits, and then on the right side is a column with FRP wrapping. That's one option. There are some papers that address this type of retrofit. There are some detailings that are recommended. For example, when you have a rectangular column, just a very simple detailing that increases your performance is rounding up the corners. Because in the corners you could have concentrated effects, so you round them up before putting the FRP. So that's a good detailing. Now steel jackets, those are useful when you have a higher charge that is close in or near contact, because that would prevent more localized type of damage. Now, one very important thing to keep in mind with steel jackets in particular is that they might be prone to direct shear failure. And I think that was mentioned in a couple of presentations earlier. In fact, Ganesh showed a picture of one where, you could put your steel jacket and now you create a very rigid element, but then at the point where the jacket stops, whether it's at the floor or at the top, typically it will be at the floor because it's closer to where your charge is, then you could have a direct shear failure there. Now, there are different ways of preventing that, and you could extend that steel jacket and put some angles and then put some anchors from those angles to the ground to prevent that direct shear failure. But that's a very important thing to keep in mind. Detailing the welds of the steel jackets also, and also the effect of that stiffening and strengthening of that column on your overall system, not just for blast but for other reasons. Right now, if you think of your structure under seismic load, Now you have a column, whether you did it for one or a few of them, that are stronger, are stiffer than what you originally was designed, what that structure was designed. So it may change the way the structure behaves, and it may cause, again, unintended type of responses. For beams and slabs, again, this is an example, I guess, for an exterior load. So you are putting the retrofit on the bottom part of the beam. Now you have an interior load, it will be the other way, right? But this type of retrofit typically will go on the tension side. Options for increasing the flexural capacity are FRP, steel plates. You can also add more concrete, whether it is with shotcrete or just with formwork, but additional concrete with additional reinforcement. Now, similar issues. Have to make sure that if you're increasing your flexural capacity, again, that will increase your shear demands. Now, in the case of beams, you can also increase your shear capacity with FRP or steel plates, on the sides of the beam and anchored. But now that's how do you do that for slabs? So that's very challenging, or I would say not practical, right? So for slabs, it gets tricky. And you have to see whether even that retrofit will work at all or not. Again, I'm saying not necessarily whether it would work for flexure. It may work for flexure, but whether it may work for shear, the original capacity of that member. Another example, composite backing wall system. So this could be whether it's a concrete wall or a reinforced masonry wall. So it consists of adding a layer of concrete with reinforcement. There is a document from the UFC, a UFC document, 402-302. I don't think it's actively maintained anymore, so it's kind of older, and again, it's not updated. But this document provides some general details for different retrofits. This is just one of them. And as shown in the figure, the concept, again, is adding that layer of concrete with reinforcement and some detailing, because you need to anchor. Obviously, you need some connection at the top, at the bottom. You can use some threaded rods or other type of dowels. Now, the one on the left is not composite with the CMU or concrete wall, again, because as you can see, there's nothing, no shear connectors between them. Now, the figures on the right side, they show a concept where you can drill dowels, right? So to help that layer of concrete add composite, and that way you're increasing your moment arm, and you can get a much more efficient retrofit. Now you can, if you are worried about, or your demand is exterior blast load, you would generally put it on the interior side, right? That's when you're increasing your positive moment capacity. If it is on the interior, if the blast load is on the interior, you'll likely want to put it on the exterior side. And I mean, you could potentially put it on both sides, right? Another, this one, FRP, there's a lot of publications on FRP, and there's a lot of presentations on FRP. And FRP can increase the flexural capacity, the flexural strength of concrete elements or masonry elements. However, there's a couple of things to keep in mind. FRP is very strong, it's very stiff, but it's not ductile. So I would say the ductility is very limited. So that's something to keep in mind. Once you reach that ultimate flexural capacity, it will, depending on the response limit that you're looking at, but you'll see that response limits won't go typically beyond a ductility ratio of 1.5 or something like that. So that's one thing to keep in mind. And the other one that I mentioned earlier, and I will keep mentioning because it's kind of common for all the retrofits, which is the shear. Again, this increases your flexural capacity, but you're not increasing your shear capacity with this, again, unless it's a beam or a column, where you can do that. There are several published papers on methods for FRP, but there is a document from the ACI 370 committee is working on. I don't know the timeline when it will be published, but hopefully soon. But there is a document, it's a report, because there is ACI 440 for FRP, but this would be a report specifically for blast design for FRP. Another retrofit, now we're moving a little bit more onto retrofits for CMU, for masonry walls. So bonded polymer, that's one that's also being used a lot. There's a lot of testing. Now, bonded polymer can be applied with a spray or trowel-on application. The picture there on the top is a spray-on application. It has a much lower strength than FRP, but it's much more ductile. In addition, it may reduce the hazard associated with shear failure because at some point it may act almost like a tension membrane once you lose the flexural capacity. However, again, you have to keep in mind that the capacity or the strength is much lower. So typically you will see these retrofits as an option for relatively weak walls, like unreinforced CME walls. You won't see it for a reinforced CME wall because that reinforced CME wall probably is already stronger. Like the bonded polymer is not going to do much to a reinforced CME wall. But for an unreinforced and a relatively low blast load, that can work. It's for non-load bearing walls because the deflections will be higher. FRP, you can get lower deflections. But with a bonded polymer, again, it's a flexible type of retrofit, so you will go large components, so that means you cannot use it for load-bearing wall. Now, each of these retrofits have their details to keep in mind, right? So most analysis, the analysis and design methods for bonded polymer are based on proprietary either methods or characteristics. So you won't see. There is some effort for the FRP, again, as I said, to develop a document that can be used for different types of FRP products, but I don't think you will see that for bonded polymer. They are very specific to each product. And there are no response criteria. You won't find response limits on PDC TR 608 or any other document. Again, they are specific for the product. Now, this can be prone to localized strain concentrations, and what I mean with that is, so in this picture, you can see two masonry walls with bonded polymer. This is after test pictures. And on the picture on the left, there is a multiple crack formation. So, cracks in different, along the length of the wall. So it's a better distribution of strains. But on the one in the center, the crack was concentrated in the center at a midspan, and that was a premature failure, a rupture of the polymer, right? Because all the strain is concentrated on that single crack. Now, predicting when you're going to get multiple crack formation or single crack formation is very difficult. And people that have done those tests, it's almost random. Like you cannot, because there's so much variability in the construction of CMU walls, so predicting that is extremely difficult. So that's a big challenge because, again, the behavior is very different. And when I was talking about shear failure earlier, again, that's an example is on the right picture. You can get that shows the shear failure, but at that point, again, depends if blast block is already gone. You can hold onto that debris with that bonded polymer because it's more flexible. A few other ones, and now I'm just going to show some pictures, really just to get faster to the end so that we can answer some questions. Steel straps, the concept, similar to FRP, that essentially you are adding reinforcement to a masonry wall. But of course, you put the steel straps, but then you have to put anchors so that you can develop the composite action. And again, these pictures are from the ACI 370 document. On the right side, you have retrofit adding corrugated steel panels. And same concept, you add a corrugated steel panel on the interior side or non-loaded sides of the wall, and you add sufficient connectors to develop composite action. So that panel is acting essentially like steel reinforcement. These retrofits, though, they are more like they are used. You also see them in the ASCE document for blast design of petrochemical facilities. Right? Because just the way aesthetically how they look, you probably won't see them on a on a VA or a GSA retrofit of a GSA building, right? But on petrochem, typically the owners, they won't care much about how it looks. All their buildings look ugly anyway, so they say like, just put them there. Like they don't care. It's an industrial type of building, right? It's a control room, so they really don't care much about how it looks as long as it works. This is another example directly taken from that document that I mentioned, the AEC for glass design for petrochemical facilities. So this one is adding a steel post on a CME wall. Now this one is interesting because as opposed to the other one, this is changing essentially the direction of the element, right? So you have a wall that initially supposed to span vertically, but now you install these posts, which obviously is not shown here, but those posts need to be connected at the, actually, if you look really close at the bottom, here, right, then you have connections to the floor, and the same at the top, you have to connect to the diaphragm, right? So you have these steel posts that are connected to the CMU wall, but they are not connected to develop a composite action or anything like that, but just to hold on the wall. And now the wall, because you put these tubes close enough, now the wall spans horizontally now between these posts. Now you can put the posts on either side of the wall, on the loaded side or on the non-loaded side. Of course, if you put it on the non-loaded side, it's easier because your wall is bearing, right, direct bearing on your post. But you can also put it on the other side, but then you have to hold them. And if you just use anchors that they don't go all the way through, it's going to be very difficult to get enough capacity. So it's just better to use through bolts at that point. And this is the final one. So another retrofit that is also covered, again very briefly and in general terms in that document, is unbonded membrane catch systems. Now, I don't know if that's a retrofit, technically speaking, because you're not doing anything to the wall. The concept here is you are just trying to, like the name says, right? It's unbonded, so it's not bonded to the wall, and it's a catch system. So you're trying to catch the debris from the wall. So you're letting the wall just fail, but all you're trying to do is catch the debris so that debris doesn't fly in. So as it says, does not increase the strength of the wall. Now because that catch system is going to work as a tension membrane, the most important part here are the connections. The top and the bottom, those connections need to be detailed very carefully so that you can develop that tension capacity. Now, it's not just the capacity of your anchors. Sometimes even the shape of those plates that are shown there in green, that it's better to round them, because if you round them, then they can produce tearing of that material. Again, a lot of detailing to develop and avoid tearing. Now, in terms of the material itself, there are different options. And there are different documents, that cover, there are papers and reports on this type of retrofits. And options include geotextile. That's the most common, I guess, that material used for this type of retrofit. But the steel sheets and some polymers. And believe it or not, like I've seen a report, actually from tests done by AFRL on polymer. Essentially, it's the material that uses on shower curtains, right? But very heavy, thick plastic shower curtains, and they have anchored, top and bottom, put it behind CME walls, loaded, and they actually worked. So, now, whenever we say work, it's always relative, right? Work for what? For what blast load? For what intensity? If you put a heavy blast load, obviously, whatever retrofit you put there, it's going to overload it. So always take it with a grain of salt when people say, oh, have a blast retrofit. Well, yeah, blast retrofit for what type of walls, for what, what type of blast load, what intensity of blast load, what performance level was. So, just final remarks. As I said earlier, most of these retrofits increase your flexural capacity. The one takeaway is that you have to look for shear. That's always the shear and the connections. Also look for potential load redistributions, effect of the additional mass for some of them, with shotcrete or a backing wall, for example, something that is heavy. And finally, just a general recommendation, all these retrofits, design of these retrofits is complex. It has a lot of nuance. So you want to get the proper experienced structural blast specialist to do that type of design. And with that, thank you very much for your attention.